What a fantastic idea! The Rattlegram app for smartphones transmits data using our radio's microphones and loudspeakers, with more than double the speed of APRS. How is this possible without cables to the handheld? And what is the relation of this project with Wi-Fi, 4G and 5G? Stay with me, I will tell you an interesting story. Hello wireless enthusiasts. Here is the channel with a strange Swiss distortion in the signal, with a new video around wireless and other exciting stuff. Make sure you subscribe if you do not want to miss the following emissions. I found this app in Steve Stroh's Zero Retries newsletter, which covers digital ham radio topics. And Ahmed, the German-based inventor of Rattlegram, helped me understand this complex topic. Let's look at how Rattlegram works. I open the app and type a text into my smartphone. The same app on the second smartphone is in listening mode. Both are connected via two 70 cm handhelds. Now I hit the PTT on one walkie-talkie and press transmit on the app. We hear a short signal and the text is already readable on the second smartphone. I prepared a message just for you. Who is the first to decode it and write it in the comments? You can argue we had digital modes since 1980. What is new about this app? The first thing, its raw transfer speed is around 2800 bits per second, with a bandwidth of 1600 Hz. Pretty fast. APRS usually is 1200 bits per second. The second is that we do not need a cable to connect the walkie-talkies. It also works with PMR or GPRS handhelds, or, as you saw before, on YouTube. And third, and most important, it uses orthogonal frequency division multiplexing or OFDM modulation, which is the hottest modulation of our time. Wi-Fi, 4G and 5G protocols all use this modulation. So I thought we, as wireless enthusiasts, should understand it. Unfortunately, it is a bit more complex than just amplitude modulation. But I propose a joint journey from amplitude modulation to OFDM with stops at interesting points like FM, SSB, FSK, etc. In future videos we will build a transmitter and a receiver for each modulation to play with. But because we live in modern times, we will use GNU radio instead of transistors, resistors, capacitors and inductors. Like that, all of us can participate without additional cost. And if you do it right, our software devices should be able to interact with our real-world gear. What do you think? Will you join? And which modulation interests you? Coming back to the topic, the most pressing questions are, of course, why is OFDM so widely used? And what is the difference between our well-known modulations and OFDM? Before we even start, we have to introduce the concept of a symbol. In FSK, for example, each bit is a symbol because a symbol only carries one bit. As we will later see, modern modulations carry many more bits per symbol. The first problem OFDM attacks is reflections. We all know that our signals often do not travel straight from the transmitter to the receiver. Often the signal is reflected on walls or mountains, or in the ionosphere. Because they have to travel a longer distance, the reflected signals arrive later at the receiver. Why is this a problem? Let's assume we want to build a 2800 bits per second channel using FSK. At that speed, each symbol is 357 microseconds long. Let's assume a reflected sound signal has to travel only 10 centimeters longer than the direct signal. Because sound travels at around 330 meters per second, this signal arrives 300 microseconds later at the receiver. Sounds like not a big problem, right? Let's look at what happens at the receiver. This is the original signal and here is the delayed one. The receiver adds both because they are on the same frequency. So the delayed signal can disturb the next symbol. Not good. It gets even worse with a strong reflection or several reflections. So what to do? One possibility is to add a gap of 300 microseconds between the symbols. Then the delayed signal would not disturb the next symbol anymore. But we would lose 50% of our channel capacity because it would lead to a lower bit rate. The same applies to radio waves. Because the speed of light is much faster, the effect is only on higher data rates. Still, current Wi-Fi and mobile phones easily reach such rates. Fortunately, clever guys found a simple solution. They divide the available bandwidth into many small channels. Because these channels are much narrower, they do not allow high data rates, but their capacities add up. They call their invention OFDM. Now we already know the meaning of frequency division multiplexing. Hams who know FT4 or FT8 know this part of OFDM. In FT4 and FT8 we see a lot of parallel information streams on one 3 kHz SSB channel. Each FT8 stream has only a 50 Hz bandwidth. Rattlegram goes much further and uses 256 parallel streams. Each stream has a bandwidth of only 6.25 Hz. To get the same throughput, we can reduce each stream's speed by 256. Exactly what we need. One symbol in Rattlegram is 180 milliseconds long. So the 0.3 milliseconds delay only disturbs the next symbol for a short time. If we added a short delay after each symbol, the delayed signal would not hurt at all. Very clever. Rattlegram invests 20 of the 180 milliseconds for this protection. That is what I call a plan. Divide the available bandwidth into 256 tiny parallel channels. Reduce the symbol rate of these channels and add a short delay between the symbols. All our problems are solved, right? Right, but we created new problems. Did you ever see a filter with 6.25 Hz bandwidth? And how big and expensive would it be? And what about 256 of them? And what about channel separation? We all know that if we have two strong signals nearby, it is hard to distinguish between them. So this idea seems to be good in theory. Must have been a physicist or a mathematician who invented it. An engineer would never have such stupid ideas, right? Right until the software-defined radio was invented. Then things changed, as Rattlegram shows. Mathematicians found a formula that creates many parallel channels that do not disturb adjacent channels. What is impossible in our analog world is possible in mathematics. This is where the orthogonal comes from, by the way. They use synchronized designer signals particularly created for that purpose. Orthogonal signals do not disturb adjacent channels. In FT8, each channel belongs to a different station, which cannot be synchronized. This is why it needs broader channels. This formula is called inverse Fourier transform. It creates values that, if sent to a digital to analog converter, become a signal that can drive a loudspeaker. I call it black magic. They call it an OFDM encoder. On the receiver side, they use an analog to digital converter and use what they call the inverse function, which, as an output, gives us back the 256 parallel signals. Cool! Without one capacitor or inductor. And with a bandwidth of only 6.25 Hz per channel. Incredible for an analog guy like me. We still have an enemy to conquer: noise. If we have weak signals, it is easily possible that a few of the many bits are disturbed, and the received data is different from the one sent. This is not acceptable in digital signals. So, what to do? From earlier days, we know a simple trick called parity. We added a bit at the end of each byte, calculated from the bits before. If one bit was disturbed, the receiver could detect it and knew something is wrong. I cannot trust the received data. But it did not know where the error was. Not very valuable for a system like Rattlegram, where we have no backchannel to ask for retransmission. In the past, we had situations without a backchannel too. Transmitters were used to transmit confidential data to spies in other countries. They obviously did not have a transmitter to request a repetition of data with a parity error, because they did not want to be caught. So we used forward error correction, or FEC, where more redundancy was added. Like that, the receiver was not only able to detect disturbed messages, it also was able to rebuild them. LoRaWAN, by the way, uses the same principle for sensors without the backchannel. Of course, FEC, or redundancy, also reduces a channel's throughput. But it is necessary for noisy channels. OFDM has another ace in its sleeve. Ahmed uses QPSK, which can transmit 2 bits in one subchannel. As we all know, FSK can only transmit 1 bit per symbol. Wi-Fi and other modern systems use even more potent schemes called quadrature amplitude modulation, or QAM. They go up to 6 bits per subchannel. You can imagine how fast such channels are. And because of the increased throughput the many parallel channels provide, we can sacrifice a part of the additional speed for transmission reliability. Because Rattlegram has no backchannel to ask for retransmission, Ahmed decided to add 50% of redundancy. Summarized, with Rattlegram we can study this fundamental protocol and do some experiments. And because it uses acoustics with low speed of sound, we see all the effects already at low speed signals. This has the significant advantage of using cheap instruments for our experiments. And we can try to optimize the protocol for performance on our standard channels by extending the bandwidth or adding a backchannel. And with a backchannel we probably could use higher order QAM to boost speed on our connections. What do you think? And do you know of ham radio protocols using OFDM? That is all for today. As always, you find all the relevant links in the description. 73 to everybody, and please consider supporting the channel by using the links in the description. See you in the next episode.